Welcome back to Physics with Miss B, and today we are doing January 2022 CSEC Physics Paper 2. Okay, so difficulty level of this paper to me, out of, let's say, 1 to 5, 5 being the highest and the hardest or most difficult, I would give this one, let's say, around 3.5. 3.5. Reason being is that you had to actually derive an equation, 1 and 2. You had to remember, this one is a gas law. You had to remember to convert your temperatures into Kelvin. And 3, the graph wasn't a straightforward graph. You could have made a mistake really easily in your excitement and anxiousness, right? It wasn't really straightforward, and they didn't give you any calibration, any scale for your calibration. So you would have had to spend a really good amount of time doing this. So in this instance, I would have told you to do the easier questions first. So let's go. Here we have figure 1 shows the arrangement of the particles used to investigate how the mixture of a fixed mass of gas varies with the temperature of the gas. Now the cylinder is made of a very strong material which allows it to withstand high pressures, and it is sealed so that there are no leaks. A temperature sensor is placed inside the cylinder to give an accurate record of the temperature of the gas over a wide range of temperatures. A pressure gauge is also placed in the cylinder to record the pressure readings. So this is exploring the pressure law, and the title of the figure says apparatus used to show the relationship between the pressure and the temperature of a gas. No, it says use the kinetic theory of gases to explain why the pressure of the gas increases as the temperature rises. Okay, well, I took this straight out the book, but we all know if you have a fixed volume, because that's basically what the temperature law says. If you have a fixed volume of gas, if you raise the temperature, pressure going to increase because this is not going to expand, right? It's a fixed volume, constant volume. So as the temperature of a gas rises, the average speed of its molecules increases, and therefore the force exerted by its molecules on the walls is greater. If the volume remains constant, the area of the walls is constant. Since the force increases as the area remains constant, the pressure on the walls would increase. So it says here the question was used kinetic theory of gases to explain why the pressure of the gas increases as the temperature rises, and this is exactly why. Okay. Then we have given a table showing the results of pressure and temperature. The table 1 shows the results obtained when the experiment was carried out to investigate the variation of the pressure with the temperature in degrees Celsius and pressure is in pascals when the gas is heated. It says use the results from the table 1 to plot a graph of pressure PA against temperature degrees Celsius on the grid above on page 7. So I put the graph right next to it, and it was a landscape graph. You were given, the one thing they gave you were the axes. They divided up the graph for you because it was pretty, it's doable, but the thing is your time frame given for something like this, there are a lot of thoughts that had to be put into this. For instance, you could have made a mistake. You could have plotted 1.1 every 2 and then forgotten that you're actually going up in 0.1 each time. Some people might have been like, oh, this is easy, 1 next to 1.1 next to 1.2 next to 1.3, and that would have messed up your results a lot, right? So in this case, you're taking up the whole graph, but your plotting would not, because when it comes to pressure temperature graphs, especially when they want you to extrapolate down to the x-axis, it's going to be a wide extrapolation because it's going to take up a lot of the negative side over here to get to where I want it to be. So what I did is every 5 on the y-axis. Every 5 spaces was 0.1 for me. They had 17 spaces and it went up to 1.1, so 0.1 was used for each space. Okay, and usually to find these out to see if it was good to go, I counted the spaces and then I divided by 1.7, and then I saw that I would have gotten a rounded nice figure like 0.1 for each space, so it was nice. So most of the graph plotting for me was up here, and it's good if you have a scale that's easy to read. Now for the x-axis, now I did every 2 spaces with 10. You could have do it like this. I don't usually do this, but because I usually give like a 5 spaces, maybe 10, but this was good. But you could have also done every 2 big spaces, every 2 centimeters here, 2 boxes, 100. You could have done it like that, because then each one would have been 10. So been 10, 20, so in here would have been 50. This would have been 150, then 200 right here. So however, just make sure you calibrate properly and equally, right? Calibrate equally, because if you have 100 by 1 centimeter space, or 1 centimeter here, or 1 box, and then the next 2 boxes is 200, we have a problem because we don't have a graph break here. They expect you to plot all your points equally. Okay, so I did every 2 spaces. You could, every 2 small spaces. You could have done every 2 large spaces for 100, then 200, then 300, something like that. But yeah, and then once you put your positive values on the right and negative values gone in the left. And as you can see, I did not number or give a value to each point, seeing as how we didn't need any points over here, excepting for when we had an intersection on the x-axis, and that's what I did. So in plotting, I plotted 20, 25. So you have 10, 20, 25. So when the temperature was 25 degrees Celsius, it was 1.2. And when it was 50 degrees Celsius, right? When it was 50 degrees Celsius, it was 1.3. At 75, we look through here, we see that this is 70, 75, 80. At 75, it was 1.4. And then down here, come down here, at 100, it was 1.5. Come up here. At 125, because this is 120 and 130. At 125, it was 1.6. And at 150 here, it was 1.7. So sweet, sweet, sweet deal. Nice and easy to plot. Never give yourself a headache when you're plotting graphs. Make sure you can read your scales properly. And I have shown you many times how to calculate how much each point is worth on a scale. I'm going to show you again, because if you're new and you've never been through my videos, it's only fair that I show you. So here we go. So if you want to know what each point in between here is equal to, just subtract the smaller number from the larger number within the range. So you want to know what each small point in here is equal to. You could say, well, 0.1 minus 0. Or you could even say 0.2 minus 0.1. You're going to give the same thing, the same outcome. So you would say 0.2 minus 0.1. And then you divide by the amount of spaces, 1, 2, 3, 4, 5. And so we see here we get 0.1 divided by 5. Okay? So 0.1 divided by 5 would tell us that each space is 0.02. Okay, so that's how you work it out. Each space is 0.02. So this would be 0.12, 0.14, 0.16, and then 0.18, then 0.2. That's how you know you're going correct. And you do the same thing between here. So this is from 0 to 10. And so we say 10. So this is for here now. This space here. And you say 10 minus 0. We have two spaces in here, so we just want to know what the 1 point is. So divide by two spaces, and we have 10 over 2, and that will be 5. So every space is 5. So 5, 10, keep adding 5, 15, 20, 25, 30, 35. So that's how you do it. That's how you do it, okay? Alright, so now that we have that, I'll get rid of this to keep the graph clean. And it says that once you're finished plotting your points, they said to extrapolate the line to meet the temperature axis and mark this point X on your graph. So, and then it says state the temperature value at this point and the name given to this temperature value. So you would know, and you could forget this real easily, yeah? Wherever we cross the x-axis, well, the x-axis is the temperature axis, and I had everything labeled for you. You're supposed to say at this point right here, right, I'm going to label it X, right? No, because I'm not writing on paper, my the pen, the broadness of the pen takes over, but right here in this area, that's where X is, okay? So you put your X there. I guess you're getting a little point for that. Yeah, because it's 3 points. And then it says, what is the temperature value at this point? Well, I got approximately, I just approximated because I know it's supposed to be absolute zero temperature. And on the I did this graph on paper, you know, just to manipulate it well on the screen, because sometimes the screen doesn't do what it's supposed to do. But on the paper, I got very close to 273, negative 273 degrees Celsius, which is basically 0 K. Some of you might get 280, negative 280. That's when you're within the range, okay? And remember that this was an experiment done, so we have to account for little discrepancies here and there. You know, probably poorly calibrated instruments or human error when reading the pressure gauge and things like that, or the temperature gauge. So a lot of that we have to account for. So I got very close on my graph to negative 273 degrees Celsius. That's why I put this here. And so I wrote it down as negative 273 degrees Celsius. Now note again, if you get negative 280 degrees Celsius, that's fine, okay? And so I have 0 K here. So I put 0 K to show the relationship between degrees Celsius and Kelvin. So to get my 0 K, I would have added 273 to negative 273. And that's how you convert between degrees Celsius to Kelvin. So to get to Kelvin, you would add 273 to whatever value degrees Celsius is. And to go backwards, to go from Kelvin to Celsius, you do the opposite. You subtract 273. So this is 0 K. And it says name the temperature value, and this temperature value, 0 kelvins, is referred to as absolute zero temperature. So you see the relationship, negative 273 degrees Celsius and 0 kelvins are equal, they are equivalent, and they represent the term absolute zero temperature. This is where it is taught and said that all particles are not moving, they have no energy. Now C says use the graph to determine the gradient of the graph. Simple. All you gotta do is find 2 points on the line that you were not given in the table. Okay? And so I use this point in black, and then I use this point up here. So this point is very easy to find the coordinates. So this, I label this as 2, my point 2, and this as point 1. And so I have here y2 is definitely equal to 1.1 times 10 to the 5 pascals. So that's something we need to remember, that the pressure was multiplied by 10 to the 5. And it says it here. And then of course 1.1 times 10 to the 5 pascals, or the x-axis, it comes to 0. So 0 degrees Celsius. Then my next point was really pretty close to the top point, and this one was given 1. And so the y coordinates at this point, y1 was equal to 1.66 times 10 to the 5 pascals. And when you come right down, again, I didn't put my perforated lines. You know why? Because of the fact that my lines were not falling. Because of how this test was scanned, the computer couldn't determine. I just couldn't do what a human being would do, which is manipulate the situation where you could just figure it out, like twist the paper to fit your line. So as you can see here, the x-axis, the x value or the x coordinate is definitely 140 degrees Celsius, and when you go across, try my best here. When you go across, it will be 1.66. So each point, again, remember, was 0.02. So this will be 1.62, 1.64, 1.66. So that will be the coordinate for y1, my y1. Okay? Usually your CXC one, they want you to have a nice triangle. Our triangle is going to be small because of the limited space we have. So you want to have your triangle drawn in this perforated line. So when you look for your coordinates, make sure you always put your perforated lines, one going across and one coming down to meet the x-axis. And same thing here. So we have a nice triangle. So you should get a point for that. But this entire thing is 5 marks. You should have calculation. So remember, to determine the slope of a line, it's the difference in y values of y coordinates divided by the difference in x coordinates, and these are the coordinates that you would have determined for the points that you pick on your line. These are entirely new coordinates that you pick from your line, and then from there you put them in. So since it's times 10 to the 5, I just put these two numbers together to find the difference, keeping it by times 10 to the 5, because I didn't want to have a lot of calculation to do or calculating to do, and the answer will come out just fine. If you wanted to, you could have actually written it as you could have said 1, so 1, 2, 3, 4, 5. This is the actual number when you multiply it by 10 to the 5 minus, and we count from where the point moving. So we count here. Let me see. Oh, the point was between 1, so this would be 1, 2, 3, 4, 5, right? And this would be 1, 2, 3, 4, 5, and all of this would be, of course, Pascal. So we have to indicate the unit. Always carry units, and then we could show the calculation down here, which is easy, 140 degrees Celsius, and then you would see that when you subtract this 110,000 from 166,000, you will get let me do it here. So 166,123 minus 111,234 zeros, you get 56,000, right? Which is exactly this. So 0.56 times 10 to the 5. If you move that 0.5 times to the right, you get, let's go, we're going to start counting now because you're moving the points. This is 1, 2, 3, 4, 5, right? So you get the same number divided by 140. I got 400 pascals per degree Celsius. Now this is quite peculiar, seeing as how in the gas laws, when you're dealing with pressure and temperature, your temperature must be in kelvins. But we're going to just follow the directions. This is what I said to do. Find the slope of the line given the cards that you were given for this question, and so we should get 400 pascals per degree Celsius. But don't let this fool you for the upcoming questions, okay? Anyway, so the sentence below is an incomplete statement of the pressure law. Complete the statement by filling in the blank spaces. For a fixed mass of gas at constant volume, the pressure is directly proportional to the absolute temperature of the gas. Okay. Then in E, they went on to, after they tell you to divide pressure by temperature in degrees Celsius, they went on to ask you to do the same thing here. But if you do that here, if you don't convert to Kelvins here, we're going to have a problem, you know. So, you know, the question was, that's why I give it a difficulty, I think, of what I told you, 4.5. Because question 1 almost will have you drowning. So it says, in the experiment on page 6, the pressure of the gas is at 1.2 times 10 to the 5 pascals at a temperature of 25 degrees Celsius. When the cylinder is heated, the pressure reaches 2.1 times 10 to the 5 pascals. So this was never recorded. We just went all the way up to 1.7. Now it says calculate the pressure of the gas in degrees Celsius calculate the temperature of the gas in degrees Celsius at this pressure. So what you do always is list out your variables. Never go and have it in your mind and say, oh, I know what this means. So as bright as you be, you're on the exam as bright as you are, you're on the exam conditions, and your anxiety levels are up. You're anxious, you know, so be very cautious about how you list out your things and about how you answer your questions. So when you list out your things, you can clearly see what they're asking for. We're looking for T2. This is the after. So this is the before. We have our variables from before, and our variables now we have pressure. We want to find out after. What's the temperature after? So again, we know according to the pressure law, when you increase the temperature, the pressure is going to increase, right? So the pressure law, we write it out as P1 over T1 equal to P2 over T2. We substitute, we transpose in for T2. So how we transpose for T2? We move it across, we move up T2, bring down, so we have it here. So we have to move up T2, move down P1, and then we move up T1. So it's like a bunch of diagonals we're writing there. And you know, it's very important to know how to transpose in physics, by the way. A lot of things deal with transposition. So I'm going to show you how we go if you don't know. So you have P1 over T1 equal to P2 over T2. Now I do this, some of you might know how to do this already, but remember there are some people that don't know how to do it. That's why I'm very thorough. I try to be as thorough as possible. So if you wanted T2, the first thing you have to realize, whenever you're looking for a variable and it's in the denominator, you need to move it out to the denominator one time, because we don't want it there, we want it in the numerator. So we can move T2 because it's dividing, doing the dividing, you multiply, you do the opposite of division and multiply. So T2 will be gone from the right hand side, and we can end up with T2 P1 over T1 equal to P2. But we want T2, not P2. So we have to go again. So we have T1. We want to get rid of the friends T1 and P1. So since T1 is doing the division, we're going to multiply both sides by T1. And it's going to cancel out on the left. Now we have T2 P1 equal P2 T1. We're still looking for T2. So seeing as how P1 is being multiplied, we can divide both sides by P1, and now what we have is exactly what we need. P2 T1 over P1. That's what we're looking for, right? So given that we have this equation, we have manipulated the equation the perfect way we want it to be manipulated, and the way we want it to be done, we now can substitute our values exactly where they need to be. So we know that P2 is 2.1 times 10 to the 5, and then we know that T1 is 25 degrees Celsius. So we need to convert this to Kelvins. So by doing that, we add 273, we get 293 Kelvins, and then we divide by 1.2 times 10 to the 5 pascals. After a series of calculations, we calculate the top separate from the bottom. We get 625.8 divided by 1.2, because the 10 to the 5 cancel out. And we got kelvins here. We get 521.5 kelvins. But let's not forget the overcomplicated everything and required you to convert the temperature from kelvins to degrees Celsius. You had to do a bunch of conversions. So you first had to convert to kelvins. Then once you calculated everything and got your answer in kelvins, you had to go back to degrees Celsius by subtracting 273 from the 521.5 to get your degrees Celsius. So remember, if you have degrees Celsius, to go to kelvins, you add 273. And if you have kelvins, you do the total opposite, which is subtract 223. That's what you see happening down here. And voila, this would have given you 25 marks. They are very close to it. Okay, I hope you got this answer. We're moving on to question 2 just now. So here we have question 2, and it says, Figure 3 shows a sketch of a natural convection solar water heating system. And it says, state which feature of the solar water heating system shown in figure 3 demonstrates each of the following thermal energy principles. Now, the picture looks intimidating, eh? It looks intimidating, but they're just asking you, based on the thermal energy principles, what was done to make this apparatus workable or work efficiently. So for good absorption of heat to make the water hot, a black surface was used. Black absorbs heat really well. And then it says heat transfer by convection. Now we know, or if you don't know, convection is the transfer, is one of the ways that heat can be transferred. And the heat in this case is transferred via fluids, right? It's via fluid. The heat is transferred via matter, in this case a fluid. And the fluid could either be a gas or a liquid. And in this case, it was water. And here we have some water, and we see that the water gets really hot. So by convection currents, by convection, the transfer of convection, the heat was able to be transferred to the water. The greenhouse effect occurs when there is glass involved, and that's when infrared radiation enters it at one type of wavelength, and it gets trapped because the wavelength is changed. So this wavelength comes in, passes through the glass as short wavelengths, very short, and then it changes when it gets absorbed. It's unable to leave the glass. It gets trapped in here because the wavelengths get long. Okay? So, yes. And then good heat transfer by conduction. And that's another way that heat is transferred, via a process called conduction. And conduction occurs within solids. And the conductors here will be metals. Right, so copper is a metal. Copper tubing is a metal that enables the conduction of heat to the water. Now the next question asks, a group of students use an electrical method to calculate the specific heat capacity of a liquid. The students found that it took 400 seconds for the temperature of 0.2 kilograms of the liquid to be raised from 25 degrees Celsius to 70 degrees Celsius. The energy supplied by the immersion heater was 15.6 kilojoules during this period. Define the term specific heat capacity of a substance. Okay, the specific heat capacity of a substance is the amount of heat required to raise 1 kilogram of a substance by 1 degree Celsius. You hear how specific that is? You need a 1 kilogram, and you need to raise it by 1 degree Celsius. That's what we're looking at. That's what you need to have for 3 marks. You could also put down that the the units of the specific heat capacity. You could add it. You could say the units the units for it's the SI unit. The SI unit for specific heat capacity is joules per kilogram degree Celsius. Well, Kelvin per Kelvin. Or you could have it like this too, because I mean you don't have to worry about converting temperature to Kelvin. So have it here, kg. Okay, this is much preferred in writing, but each of them, you know. Let me take out the SI. So the units for specific heat capacity are joules per kilogram degree Celsius or joules per kilogram Kelvin. Okay. Then it says calculate the value of the specific heat capacity of the liquid. Assume that no heat was lost and ignore the heat capacity of the container. So we're doing this in a perfect system. We're ignoring a lot of things. So I decided to write down every single variable that was listed or given in the excerpt here. We were given time, 400 seconds. We were given mass, 0.2 kilograms. We were given the temperature change, and when you're calculating temperature change, you always subtract the cooler temperature from the warmer temperature. You could do final minus initial, but what will happen is that sometimes you may get a negative value, and negative numbers tend to scare students away. And the negative value is really to tell you that heat was given off, right? So to avoid scaring you off, so subtract the cooler temperature from the warmer temperature, and then we have the heat required to do this, to raise the system by 45 degrees Celsius. Heat required was 15.6 kilojoules, and converted is 15,600 joules. You get rid of the kilo by multiplying by 1,000. So if EH is equal to MCAT and you're looking for specific heat capacity, C represents specific heat capacity. So this is how it goes. This is the amount of energy. EH is the amount of heat energy required for the system. This is the mass that is being heated. This is specific heat capacity of the substance. And this is the temperature change that takes place when the substance is being heated. And they gave us the time. And in this case, they're asking for specific heat capacity. So again, we had to do a transposition. You see how transposition come into haunt you and what is very important. So to solve to make this equation equal to specific heat capacity, if we want to make this C subject of the formula, we need to get rid of all the friends. So we have mass and temperature change. Since they're being multiplied, we could divide them. And so if we divide here, we have to divide over here. And as you can see, they start to disappear. So now you have EH equal to M delta T, which you see here. That's what you get. You start to substitute your values in for the variables to replace the variables. And you have 15,600 joules divided by mass, 0.2 kilograms times temperature change, 45 degrees Celsius. And you will get 1,733.3 recurring with a dot there, or you could have a dash, either which way. Joules per kilogram degrees Celsius. So we know we're going good. 5 marks for that there. 5 marks. Alright, now it says calculate the power rating of the immersion heater. Now power rating, heat is often given off, so another expression for heat given off, would including power, would be such that P times T is equal to EH. We already calculated the heat required for the system, which was this, right? The energy, the heat energy required for the system, and what we see here, we have EH from above, well, it's given, and we have the time. So we can divide the EH by the amount of time to figure out the power. And these are the units of power. We get 39 joules per second. So I hope you got that answer. Please note that EH can be equal to a lot of things. We know EH equal to MCAT. EH could be equal to, we have PT. EH equal to EP, that's potential energy. EH could be equal to EK. EH equal to latent heat of vaporization, mass sensation, and EH will be equal to MLF, which is latent heat of fusion. All you do, if you're given EH already, you're fine. But if you're supposed to solve for like a specific heat capacity or anything like that, you will have to put out the whole thing, like a substitution. So you're like, so suppose you write this fully out, this will be actually equal to MCAT, MLF. Anyway, that's for another time. Just saying, you know, that once a system giving off heat, it could be equal to heat energy, as you can see here. So I hope you got these answers for question 2. See you around for question 3. So here we're at question 3, and it says state. So basically we're dealing with light. It says state the 2 laws of reflection. First law, the angle of incidence is equal to the angle of reflection. And the second law, the incident ray, reflected ray, and the normal at the point of incidence are on the same plane. Then it says state 4 properties of an image formed by a plane mirror. First, state 4 things of what happens to the image when it's in the mirror. 1, we know in a regular plane mirror, the image is the same size as the object. 2, the image is laterally inverted, as in it's reversed. 3, the image is virtual, it's not real. And 4, the image is the same distance perpendicularly behind the mirror plane as the object is in front. So if you're standing in front of a mirror, if you're 1 meter away from the mirror plane, your image is also 1 meter away from the mirror plane in the back. Okay? Then Maxwell, it says here, Maxwell washed his face at the restroom sink in his favorite restaurant. Looking into the mirror, he saw the image of the clock on the wall as shown in figure 4. So this is figure 4 right here. And what I did is I just rotated the mirror 180 degrees. Rotated the drawing so you could determine what the time really is. It's like a reverse. And so if you wanted to tell the time, if you didn't know, you could have turned, if you had the test paper in front of you, turn it over and look for the tracing on the back of this. Like literally flip the entire paper over and you will see that you're going to get this right here. So the actual time shown on the clock is 10 past 10. 10:10. Now the sad part is that a lot of children don't know how to read analog clocks. I mean, with the use of cell phones and you know, no digital phones, you have your Apple Watch, you have your this watch, all sorts of things. Most children don't know how to read analog clocks. It's going out. Children learn it and sometimes forget it. So if you didn't know how to read the analog clock, make it worse. There are no numbers here. You know, I growing up, I had a really hard time understanding these things, especially when they just used to have like a dot. Sometimes they didn't have these strikes. It's a dot or just nothing at all. And you're expected to remember the positions. Like, how lazy can you get? Just put the numbers. So, sorry to those people who don't know how to read analog clocks. But yeah, so the time is actually 10. This is 10, so this is 9. Every quarter, you have 12, and then 3, then 6, then 9. And so we know here this is on, after 9 is 10. So the shorthand is on 10. And then it's past 12, so this is 5 minutes, 10 minutes. So 10 past 10 or 10:10. Yeah, that's the time. Okay, then they come up with the hard train to be had. This would ask you to derive the formula. So you had to know something before you even answer this question. So it says the refractive index n is defined as the ratio of the speed of light in air to the speed of light in a medium. You have n is equal to V A represents air, and Vm, m represents the medium. So using this definition for the refractive index and the relationship between wavelength, frequency, and speed for a wave, derive the following formulas. So this where n, the refractive index of the medium, is equal to the wavelength of the wave in air divided by the wavelength of the wave in the medium. Okay, so I had to go back to the drawing board, right? I said there was much help here. So you pretty much had to know something. So it says, for light traveling from one medium to another, the ratio of sine of I, of angle I, the incidence, divided by the sine of R is the refractive index for the second medium relative to the first. So once you know this, you will say, well, the second medium, I could relate the second medium to that M, and the first medium to that of A, which is air, divided by, so basically you flip the script when it is equated to speed, which is VA over VM, right? So in this case we have, let me write it. We have here N, the refractive index of the medium, could be like glass, and then we have the refractive index of light in air. Let's just say that, the wave in air, equal to the ratio of it flips, so the speed of the light in air over the speed of the light in the medium, right? So it's the reverse. So it says is the refractive index of the second medium, so relative to the first. So flip it. So in other words, this would have been sine 1 and this is sine 2. Okay, that's basically what it's saying. So for the wavelength of a wave traveling from one medium to another, the ratio is given such that wavelength in air divided by the wavelength in the medium is equal to the refractive index of the second medium relative to the first. So you see there? That's how it is, right? So in this case we're using wavelength. And if, well, we know, well, we don't know, but the refractive index of light, sorry, the refractive index of air, right, is actually 1. So given that, we could just ignore the refractive index of air, because then anything divided by 1 will give you back that value. You will have the refractive index of light, well, the refractive index of the medium is equal to the wavelength of light, of the electromagnetic wave in air, divided by the electromagnetic wave length of sorry, Lord of mercy. So seeing as how the refractive index of air is equal to 1, then we could get rid of it, and we see here that the refractive index of the medium would therefore equal to the wavelength of the electromagnetic wave in air divided by the wavelength of the electromagnetic wave in the medium. Okay, so better written, we would say the sine of the angle in air divided by the sine of the angle in the medium. is related to the refractive index in such a way that it is the refractive index of the medium divided by the refractive index of air. And once we have this relationship, we can see that this, the refractive index, is related to all of them once it's in reverse, right? Once the second medium, so I always take second medium to be not that of air, right? So once the second medium is divided by the first, everything else would be that of, the first medium divided by the second. So for instance, the wavelength in the first medium divided by the wavelength in the second medium. That's how they are related. So second medium, the refractive index of the second medium divided by the refractive index of the first medium will be equal to the reverse of it for all of them. For wavelength, for sine of the angle, for speed of the electromagnetic wave, for frequency of the electromagnetic wave, so all of that. And then how they're related is such that the refractive index of air is always equal to 1. So once that is gone, we see that Nm is equal to lambda A over lambda B. I know it's confusing, but that's my explanation, because I didn't give you much help here, you know. All right, so given that, sorry I couldn't make it simpler. Given that, we say a beam of green laser light of wavelength 532 nanometers in air travels in water. Calculate the wavelength of the laser light in water. So we know that light slows down in denser medium, right? So air is less dense than water. So if that light leaves air to get into water, we know the light gonna slow down. Okay, the wavelength changes. The wavelength is also going to change. What doesn't change is the frequency. Okay, so we have here, we list out everything that we have. We have the wavelength, which is given, the wavelength in air. The wavelength of green light in air is 532 nanometers. We need to know what the new wavelength would be in the new medium. And that means it's supposed to slow down. So it's supposed to get a smaller number than 532. And we have here that the refractive index of A is 1. And the refractive index of the water is 1.33. So using the relationship, we know that the refractive index of medium 2 divided by the refractive index of medium 1 is equal to the wavelength of green light in medium 1 divided by the wavelength of light in medium 2. Seeing as how that the refractive index is 1, we're going to have Nm, the refractive index of medium 2, equal to lambda A divided by lambda M. Well, this is the wavelength of the light in air divided by the wavelength of the light in the medium. And seeing that, we just substitute and we start to transpose. So let me write this how it will look like. It makes sense. So we're going to have 1.33 divided by 1 equal to 532 nanometers over x. We're solving for x, so therefore x will be equal to 532 nanometers times 1 over 1.33, which is what you see here. And you will get 400 nanometers. So we're indeed correct, because the light is supposed to slow down when going from a less dense to a more dense medium. Then for special effects, a pool designer decides to fix the laser light at the bottom of a pool. He says calculate the critical angle of the water to air boundary. Now, some of you might not know what the critical angle is. So just imagine we have the pool here. This is the air. And we have the light down here. So if the light hits the normal at a specific angle known as a critical angle, right? Because the light could hit at many different angles, but if you hit it at a specific angle, this light will never leave the water. It will just run across the boundary of water, and once that means the refracted ray, sorry, it hasn't left, it's just running along the boundary of the water, and that is when we have reached a critical angle. The critical angle is the angle at which the incident rays corresponding refracted ray is at 90 degrees to the normal. See? Hence, the refracted ray runs along the boundary between the two media involved. So this is the boundary right here. So the critical angle can be determined via the following relationship, where the refractive index would be equal to sine 90, right? So divided by sine C. So this is media, this is the angle of the refracted ray in air, which is 90, that's why we have it here, and this is the angle of incidence in the second medium. So remember, we learned that the refractive index, right, in the second medium, so in this case the second medium is water, divided, so the ratio is the second medium divided by the first medium, right? So it doesn't matter which way, just remember that you have to reverse the roles when it comes to whatever you're dealing with. So in this case, we're dealing with the angles in the different media. So if you have the refractive index in water divided, the ratio here is the refractive index of water divided by the refractive index of air, then it is equal to, in this case, we're looking for the angle, the critical angle. So therefore, it's sine theta, that's the angle in air, divided by sine theta, the angle in water. Okay, so once you know that they're flipped when they are related, you're good to go. So we know the refractive index of water is 1.33. We know that of air is 1. Sine theta A, the angle, the angle, right, in air, and this case angle in air is the refracted angle, is 90. So we say sine 90 divided by the angle of incidence, in this case that's a critical angle, right? So it's sine C. So the angle is the same idea. So once you have this, in this case, I just wrote it out how they would usually just do it, like n equal to sine 90 over sine C, and I'm showing you why it's that way. So we're going to do some transpositions, and you would end up getting well, sine 90 is equal to 1. So in some books you would actually see, oh, for critical angle is index equal, refractive index equal to 1 over sine C. How? Well, the reason being is that, well, NA is equal to 1, and the angle of refraction will be equal to 90, which is 1. Sine 90, sine of 90 degrees is 1. So you're going to end up with this going and this becoming 1. So you're going to end up with N, the refractive index of the medium, equal to 1 over sine C. That's how you get it. And so with that being said, you do some transpositions, which you see here. So you're going to end up with the sine C is equal to sine of 90 is 1. And then this goes down. So this goes down, this goes up. And 1 times 1 is 1 if this goes up here. So you're going to end up with 1.33 in the denominator. Once you calculate what 1.1 divided by 1.33 is, you do the inverse of sine, which is what you see here. Right? So C will be equal to the inverse of sine 1 over 1.33, and you get 48.8 degrees. So the critical angle, this angle, will be 48.8 degrees. This is the angle that causes the light to run run perpendicular to the normal or run along the boundary. So it's not leaving the water, it's going along the boundary of the water. Now, if the angle of incidence of the laser light at the water to air surface is 52, so now suppose we increase the angle from 48.8 degrees to 52 degrees, it's a state what happens to the light at the surface of the pool. Well, when you surpass the critical angle, as in now it's no longer 48, you increase it to 52 here, guess what? This light will no longer run along the boundary, it would totally internally reflect. So now you would have some sort of a special type of reflection where the light no longer leaves the boundary, it gets trapped in the water. Okay, so the light would be totally internally reflected. In other words, the laser light's angle of incidence is greater than the critical angle of the water, hence the refracted ray would not pass out of the water. So that's what would happen. The light would be totally internally reflected, and you get 1 point for that. So this was a mouthful, and I think these questions, see where you put 4.5, these questions were not just straightforward. You had to actually know your physics. You had to understand your physics. And because, I mean, you had to actually prove a Formula 1. And instead of just going out and saying, oh, I know the formula for this, you actually had to understand why the formula was written in a certain way or why the formula is written a certain way. And if you don't know why, you can get into a lot of problems. Okay? So these are the answers for the questions number 3. Here we're at question 4. And this question dealt with linear momentum. So it says, define the term linear momentum and state its SI units. Now, the linear momentum of a body is a product of its mass and its velocity, and we could write it has units of kilograms meters per second. So that's the unit. Okay, now state the law of conservation of linear momentum. In the absence of external forces, as in a closed system, the total momentum of a body, total momentum of a system, of bodies is constant. All right, that's 3 marks. So you need to learn your laws. You need to learn your definitions. I like to ask you to write definitions. So you need to learn your laws. You need to learn your definitions. No. A truck of mass 945 kilograms heading west on the Sir George Walter Highway slammed head-on at 20 meters per second into a car of mass 630 kilograms heading east. Now that's a lot to process here. Now the first question says to calculate the initial momentum of the truck. So looking at the truck, we know the truck has a mass of 945 kilograms and it's traveling west. So for me, moving west will be moving in a negative direction. So my velocity would be negative, right? It would be negative because I'm moving in a westerly direction. Now you could make this positive and this negative, but what I did, I put my coordinates, my coordinates here. And for me, moving north is positive, moving east is positive, like on a graph, right? Going up here will be positive, and going across here will be positive. And then for me, going to the west and going to south, I made it negative, right? So you could pick whichever direction you want, but if you pick the opposite direction in terms of, if you pick not to be negative, your opposite direction should be positive. But for me, I pick my not to be positive, and so the opposite direction, which is south, will be negative. So you determine what you want. You could even use the words right, left, up, and down. So if I'm moving right, and I go based on the number line, because on a number line, if you're going right, the numbers are positive. So this will be positive for me. If I'm going left, the numbers will be negative. If I'm going up, then the numbers would be positive, and if I'm going down, the numbers would be negative, just like on a graph. So that's, I made my life easier. So in this case, I said the truck is traveling west, so my velocity is negative. So momentum is calculated by multiplying, as the definition states, by multiplying the mass by the velocity, and we get negative 18,900 kilograms meters per second. So we get rid of the negative sign and we write out what it means. We said the initial momentum of the truck was therefore 18,900 kilograms meters per second due west, right? So this is a vector quantity here, momentum. So you have to take into account the direction the object will be moving, right? So we have size and we have direction. Now, if both vehicles come to rest after the collision, calculate the initial velocity of the car. So we need to consider what happened before equal to what happened after. And remember, everything is conserved. Everything is conserved. So what all your numbers, if you calculate on the left, must be equal to whatever is on the right. So according to the question, it says, well, if both vehicles come to rest after the collision, calculate the initial velocity of the car. So we already know the velocity of the truck, and we already know the momentum of the truck. We calculate it down here, so we're doing it in parts. What we need to find out is the velocity of the car. So given the information, what we have is that we don't know the velocity of the car. We already calculated the momentum of the truck, which was the same thing. We have the mass times the velocity. We already have that. And now the after is such that the two of them, they come to rest after the collision. So the two of them come to rest after the collision. So therefore they have no velocity, none whatsoever. So in coming to rest is 0. So this whole entire equation will be equal to 0. So in doing that, we transpose. We end up with 630 kilograms times x. Since this is a negative, we add it to both sides. 18,900 kg m over s. We add it to both sides. So this entire thing will be equal to 0. So because of that, we're going to end up with something like this. And so now that we have this equal to just this, we're going to divide both sides by 630. Because this is a multiplication here. It's literally 630. Let's ignore the units so long. So this is saying 630 x is equal to 18,900. So to get rid of the 630 and just solve for x, you have to divide both sides by 630, and you will get 30 meters per second. And if you put all of this in now, if you said 30 times 630 plus negative 18,900, all of this will be equal to 0. It has to be equal to 0. Okay? That's how you do this bit. Then they give us a little extra question at the bottom here. It says the velocity of a car increases from 20 meters per second to 45 meters per second in 10 seconds. Calculate the acceleration of the car. Acceleration is actually equal to the change in velocity over time, where the change in velocity is equal to the final velocity minus the initial velocity. So we subtract 20 from 45. We end up with 25. We end up with 25 meters per second. And then we have the time, which is 10. So owing to that, you end up with 25 meters per second divided by 10, right? Is equal to 2.5 meters per second. And that'll be the unit for acceleration rate. It's an easy 3 marks, this one. Okay. Question 5. Question 5, I would say, was a question to behold. I personally don't like these questions because they're not student friendly. And the book, for this section, I personally believe that the book should make a video section, an easy to understand video section, because just drawing it doesn't cut it. You need a video section to bring it to life. So I took these pictures from a video I saw on Khan Academy because I needed the position of the hands. So let's get to that slowly. It says here, Figure 5 shows a solenoid that is connected to a battery with a current I flowing through it. And it says Figure 6 shows a cross-sectional representation of the solenoid shown in Figure 5. Now the symbol with a dot in it represents the current coming out. So this is actually like a magnified view of what's happening up here. So it represents the current coming out of the page, and the symbol X represents the current going into the page. It says draw the magnetic field lines inside and around the solenoid in the figure. So this is one you would have to incorporate the right hand grip rule, and with the right hand grip rule, I should have taken a picture of this, but I could draw fairly well. I can draw fairly well. So the right hand grip rule, because the current is coming down out of the page and down, just like I was saying, the direction of the current would be down like that. So with the right hand grip rule, what you want to do is figure out where north is. So I'm watching my hand right now, and I could draw my hand and I could draw my thumb, right? And what would happen is that if I roll my fingers down like this, see, I tell you I could draw a little bit. If I roll my fingers down like this, the direction of my nails or my fingers tells me the direction of the current, which is down, right? It's the direction of the current, which is down. And so because I have now, using my right hand, I have the direction of the current, I have simulated that. I know where my thumb is facing will be the direction of north. That's north. So once I know where north exists in this system, I can now draw my magnetic field lines, and that will be such that what I did, I drew some circles because I know the field line is going to go in a circular pattern around the wire. So this drawing is actually this simulation right here. If you complete it, if you bring it down like this, like if you bring it down, you will see that this is actually that drawing above there. And for some students, this would have been confusing. This is actually this up there. And all you're doing is drawing the magnetic field lines in a solenoid, because this is a solenoid. And once it's not, the magnetic field lines, remember, once you have a magnet, right, not so, the magnetic field lines always go away from the north. They always travel away from the north. Yeah, I'm drawing it wrong. They always travel away from the north and they go towards the south. So the attraction between these is that the arrowhead will go from the north towards the south, right? So if you complete this, it will be like this, right? So but in a solenoid, we draw our magnetic field lines going to the north, and then what happens is that they loop over. They get stronger by looping over like this because of the wire being coiled. So this magnetic field line will form these spirals around this coil, and it makes the solenoid more effective as a electrical conductor. And so we have the direction of the field lines going straight, of course, for north, going towards it, away from the north, and then they start to coil over. They're like, "Ooh, we're a wire," you know. All right. So if you imagine a straight line wire, all right, a straight line conductor, you know, you could use your right hand. What you would do is wrap your fingers around it, and the direction of your fingers would show you the direction. Well, if you know the direction of the magnetic field, right? what would happen is that you could determine the direction of the current. In this case, the current is going north, okay, or up. Current is going up, right? So the fingers in this case in a straight wire conductor will be used. Your fingers, your 4 fingers will be used to determine the direction of the current, right? Your thumb. Now it's different for a coil. When you grip the coil, in this case, this one is the coil here. This is the simulation of the coil. When you grip it, the fingers of your right hand would travel in the direction of the current, right? So your fingers is opposite, right? And the thumb will then indicate the direction of the magnetic field. So it's a little different. When you just have a wire, you would have, you know, your finger would indicate the direction of the current, your thumb, sorry, direction of the current, and your fingers would be the direction of the fields, the magnetic fields, and it's opposite for a coil. In a coil, when you grip the coil in the direction, and you know the direction, they have the arrow here, they show you the direction of the current. It tells you that your fingers gonna simulate the direction of the current, as you see here, and your thumb will now tell you the polarity, right? Your thumb will indicate the direction of the magnetic field, and the thumb will tell you the north pole. The thumb acts and tells you where the north pole is applied, right? So that's how it's done. Now the next question says the figures below show a constant magnetic field coming out of a surface as indicated by the symbol. So this dot in a circle tells us that the magnetic fields are coming out towards us. They're coming out here. They're coming towards us out of the page. So if I just draw 3, that's enough. Let me draw 3, that's enough. So these are the magnetic field lines coming towards us, right? And so it says figure 7 and figure 8 show a straight metal wire AB moving across the magnetic field in the direction shown by the arrows. So using this hand, we see that if it's the hand usually is FBI, right? So the thumb is the force causing the wire to move up, right? Or it shows the motion of the wire, which is in this case up, right? So that's why I have the force here. B represents the direction of the magnetic field lines, and you always point it coming away from the north, going towards the southern direction. So they're telling us that these field lines are coming towards us. So that's where the finger is pointing towards us. So if the metal wire is moving up, as in it is cutting across these field lines, moving up, you're cutting across the field lines, right? If it's moving up and the magnetic field line is coming towards us, then the current will be moving to the right, right? You can see here the current going to be moving to the right. Now imagine all I did was flip this in the direction of the wire here. So the wire now is again cutting the field lines by moving across, cutting across the field lines, and it's showing you that it's moving across. So if I draw the field line here, that wire, if it's moving this way, it's going to cut across the field lines at some point. It's going to cut right across them. And so if the motion of the wire is moving in this direction, okay, and again the field lines are coming towards us, this is coming towards us here, towards us. Let me draw it a little better. So the finger is coming to you. Just imagine it's coming to you. I try my best in trying to get a picture. Took me forever to get a picture like this. So just imagine it's coming to you, which is this finger coming out of the page to you. And so if that's the case, the direction of the current would now be going, down, right? So your thumb finger is F, right? Your second finger or index finger is B, and this is I, so FBI right here. So we already know the current. So this is Fleming's right hand rule, by the way. You apply Fleming's right hand rule when you want to know the direction of the induced current. And in this case, current is being induced in this wire. Then they went on to say, in figure 9, it shows the metal wire moving parallel to the magnetic field that is out of the surface. Parallel. So that means it's moving along the same direction. So this is coming. I don't even know why they didn't put the arrow. The question was already hard enough. Why? So this is moving towards you, just this in the same direction as the magnetic field. So it's not cutting the magnetic field, if you realize. Whereas this was cutting the magnetic field by moving this way, and this was cutting it. This one is now moving along the lines of the magnetic field. So this is moving this way. It's coming towards you along the magnetic field. So it's not cutting the magnetic field's lines, right? This is how I interpret it. So after we already went through this, we said complete the table below by stating the direction of the induced current in the straight metal wire in A and B. Metal wire AB. So in figure 7, the current will be going right, and in figure 8, it will be going down, and in figure 9, no current, nothing. And it says the magnitude of current if the speed was doubled, it would double for both, nothing for 9, nothing will be produced if it's moving along those lines. Then it says here, an ideal step-down transformer is used as part of a power transmission system. It has 1,980 turns in its primary coil and 180 turns in its secondary coil. 1. Calculate the maximum theoretical output voltage if the input voltage is 1,320 volts. Guess what? You have to list your stuff out. So the number of turns in the primary coil is 1980, right? And the number of turns in the secondary coil is 180. In the primary coil, the voltage is 1320, and then we want to find out what will be the voltage in the secondary coil. It's going to be less turns, less voltage. So it's a step down. So a step down transformer is one where you have let's just imagine this square with a hole in it is a transformer. It's one where you have more coils on the primary coil, the primary side or the left hand side of the transformer, as opposed to the right hand side. So it has more coils. So this is stepping down, right? And so we just substitute our values. Well, first of all, we're solving for Vs. So we're going to do a transposition. You see, nearly every question has in transposition. So you need to learn how to transpose. So again, you transpose, you have NP over NS equal to VP over VS. You transpose. So seeing as how VS is in the denominator, you want to get rid of it. Not rid of it, you want to move it in the numerator, and seeing as how it's being divided during the division, you're going to multiply both sides by it. Then VS NP over NS equal to VP. But what we're looking for is VS. So to solve for VS, we have to get rid of NP and NS. Since NP is being multiplied by VS, we're going to divide both sides by NP. And then since NS is doing division here, we're going to multiply both sides by NS. So we end up with VS is equal to VP NS over NP, right? Great. And then now that we have our values listed here, we just stick them in. 180 times 1320, we have it here. And then we have 1980 for NP. And so we're going to end up with 120 volts when we do our calculations. Then down here it says calculate the input power if a current of 135 amps flows in the primary coil. So using the primary input, the For voltage, we have 1320, right? So remember, over here will be 1320. That's how much, and that's the amount of flow of electricity. That's the flow, the intensity of the electrons being passed through this side. And we have the current applied here. So usually you will see an AC current. So the AC is 135 amps in this case. So we want to know, what was the power being given off? What's the usage? So power is also equal to I times V, is equal to current times voltage. So you multiply the current by the voltage and you get 178,200 watts. Okay, and that's the end of question 5. Okay, we're moving on to question 6. It says, what is meant by the term nucleus of an atom? Now, the nucleus of the atom is at the center of the atom. It contains protons and neutrons. Both particles have a mass of 1, and owing to this, they constitute for the entire mass of the atom. The nucleus is positively charged, because while the proton is positively charged, the neutron does not have a charge. So this positive charge is responsible for keeping the electrons, which are negatively charged, in orbit around it. So that should give it 3 marks. Then it says radon 222 is a radioactive nuclide which decays spontaneously with the emission of an alpha particle to form polonium PO. The nuclear equation representing the decay of a radon 222 nucleus is given below. We have it here. So we see we get PO, and now they want us to basically calculate A and Z, even that an alpha particle came off. Now some of you might not know how to do these equations. It's very easy. All you have to do is make sure what is on the right is on the left. So if you have 86 down here, you want a number added to 2 to equal to 86. And the number added to 2 to get for 86 is 84. 84 plus 2 is 86. So that'll be 84. And for A, you want whatever number plus 4 to give you 222, and that will be 218. Basically, the calculations right here. Okay, so or you could just remember, whenever you have 4 and 2 for alpha particle, you subtract 4 from the answer here, and you subtract 2 from this value here. So from the value here, you subtract 4, and from the value down here, you subtract 2. Right? So either which way, but I think the safest way to always go is to note and to understand that what you put in is what you're going to get out. So if you start with 222, these values must add up to 222. So whatever you put here, when added to 4, must give you 222, and likewise down here for 86. First question says, state what is meant by the term spontaneously. And I have radioactivity is a random or spontaneous process. This is due to the fact that no one knows which nuclei will decay in a given sample of a radioactive substance at any given time. That's why it's random. Then they said, use Einstein's mass energy equation to calculate the energy released during this reaction. So his equation is the change in energy is equal to the change in mass times the speed of light squared. And the change in mass is always calculated as mass before minus mass after. So seeing as how we have this equation here, I wrote it back. This equation is not on the paper, by the way. I just copied it and pasted it here, so I will have something to work with. And so we see here that, well, radon minus polonium and the alpha particles. So we're given the masses here in kilograms. So what we want to do is subtract the mass of radon, right? So it's at 368.54918 minus the sum of the masses of polonium and the alpha particle as they're given down here, all multiplied by 10 to the negative 27 kilograms. And what we will get is 0.00963 times 10 to the negative 27 kilograms. The speed of light is given, it's up here, 3 times 10 to the 8 meters per second. and we want to just calculate the change in energy. So all we do now is substitute our values. So we have 0.00963 times 10 to negative 27. Don't forget that. Times 3 times 10 to the 8 meters per second times 3 times 10 to the 8 meters per second. We must not forget that it's being squared. A lot of times we forget to square it. And what we're going to get is 8.667 times 10 to the negative 13 joules. Okay? So that should be your answer there. Now it says a fresh sample of Radon 222 gas, which has a half-life of 3.8 days, was found to have a mass of 240 grams. It says define the term half-life. But half-life is a term used to describe the amount of time a radioactive substance takes to break down by half the amount it originally was. Right? So that's the amount of time. So in this case, it's telling you that if you have 240 grams, it's going to take you 3.8 days for it to break down to 120. Right? So every 3.8 days, half of what is left will break down. So as you can see here, right? So let me say it like this. So if you have 240 grams and it breaks down to 120 grams, then it took it 3.8 days to do that. And if half of this amount now breaks down to 60 grams, then it took it 3.8 days to do that. That's the half-life. That's what half-life means. Half-life doesn't mean like, because of how the word is, it tends to mess with people's minds, like half-life. But half-life, it just means is the amount of time that a sample would take to break down to half of how much it used to be. And so every substance, every radioactive substance has different times that it would take to break down to half of what it used to be. For instance, carbon was 40 grams. Unlike radon, which takes 3.8 days, carbon to break down to 120 grams would take approximately 5,700 years. Carbon 14, that is, would take this amount of time. So, I mean, each type of radioactive sample has a definite half-life. And in this case, this is carbon 14. Well, this one is radon. So radon breaks down faster than carbon 14. Right? So that's a way we could use to determine what we're dealing with, by the way. So that was a mouthful. I'm so tired. And you should be tired after doing this exam. I think this exam was really trying. Now it says calculate the mass of radon gas remaining after 15.2 days, giving your answer to two significant figures. Well, if it takes radon 3.8 days to break down to half of how much it used to be, how many half-lives would it take it to break, to break down in 15.2 days? So basically, how many times would it take radon to break down over a span of 15.2 days? Given 3.8 days, it will break down by half. But if you give radon 15.2 days, how many times did it break down? How many times? That's what they're asking. So this is related to half-life. So how many times did it break down? It will be 4 times, because if one half-life is equal to, if one time of a breakdown is equal to 3.8 days, how many times will it break down in 15.2 days? And we see we break down 4 times in 15.2 days. 4 times, it's going to be more, right? It only take one time for it to break down in 3.8 days. So now we need to determine how many times will it break down over a span of 15.2 days. We've calculated 4 times. So how we could show this? We say it starts out with 240, and the first time 3.8, it break down after the first 3.8 days, it break down to 120, which is half of 240. Then another 3.8 days come by, and it break down to 60, which is half of 120. then another 3.8 days pass by, it can break down to 30 grams, and then half of 30 would be 15, 3.8 days again. So if you add these 3.8 days, 4 times 3.8 days will be equal to 15.2 days. So over the span of 15.2 days, we went from a mass of 240 grams to 15 grams. So it says here, each arrow represents a half-life, which is what I've shown you, which for radon 222 is 3.8 days. Hence, the amount of radon 222 left after 15.2 days will be 15 grams. That's all that's left. And that's the end of the test, folks. I hope you enjoyed my explanations. Feel free to tell me how you did, and feel free to tell me what your difficulty level is, your rating is for this test. Alright, so have a good day. Keep on studying, and bye.